Record. Right. So the thing I wanted to talk about before I got to OOP, or at least, has to do with something I keep hearing. It's not like you say one thing really, but it's more along the lines of I think people don't understand what we're doing. From year one. And what I'm talking about is when you write a program, what happens? And so I call it P call, right? P is optional, depends on your language, right? But generally, when you write a program, these set of steps have to happen before you have a working program, right? In general, okay? So the agenda is, okay, I'll move me to this. Okay, I'll just minimize you guys, put you guys over here. Hopefully I don't block anything over there, but whatever. In this nice little funny little language that I diagrams I stole from online. This diagram speaks to the hierarchy of things. All right. At the top, you have a high-level language, C, C++, Python, whatever, right? You would send that thing, you'd have things like what we're doing in class, you know, do a little swap, or something like that, right? You could write that. It looks pretty readable to humans. We then could have other kinds of languages below that on the hierarchy, like assemblies. It looks a little bit less readable. So that says load that value 0 in the register X3, and then load that value in the register X4. Then you have some kind of sequential thing going on, blah, blah, blah. Right? Assembly is specific to a chip. So if I have an Intel chip, it is specific to that particular Intel chip. You might have another thing, like if I have an i9, you might have like a I whatever number we reach. Yes, that thing that will be traumatized in year 2. The instructions which the chip supports will be different depending on what chip you have. Okay. Yes, and a big that instruction manual small. You really need to know on that instruction manual because that tiny instruction manual. Wait till you do a big chip. You'll cry. I have cried. Anyway, assembly language, when people are talking about assembly, they're talking about something that humans could still read. We used to program in it way back in the day. Before it was assembly language, again, humans used to program in it. It was called machine language. Literally, we talk in binary. Right? The assembly language used to be like a placeholder for all of the little ones and zeros. Right? That's what it used to look like. Yeah, I don't know that. Yeah, whatever. If I don't know that. So you'll see a whole bunch of ones and zeros, more or less. And the reason for that is because you have an actual interface, right? See the actual yellow line. After you get down to the ones and zeros level, now we're starting to talk about, we have to see what the machine actually looks like, the processor that we run this thing on. We have to know what the circuit looks like and also these ones and zeros to make sense, because the ones and zeros actually represent a high voltage and a low voltage, right? So when we talk about this, we're actually building on our way upward to actually build the processor on these things that run, right? And the bigger conceptual things like the multiplexer, the decoder, the adder are made up on the most understand of ands and ors and knots and boxes and whatever else, which are in turn made of transistors and yada, 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 right? So we can approach it from both ways. So back when I used to actually teach this course, we used to do both. I used to meet in the middle and make a processor by the end. So not doing that anymore. What you're saying about, right? So anyway, our agenda, at least the green set slide, is I want to talk about these steps that you go through after you have written your program, or the step that it goes through, right? And to precursor that discussion, I want to talk about interpretation versus translation. Okay. So that's literally the talk I'm going to start with before I get to OOP, because I figure this might be useful beforehand. You don't have to learn it before, but I think it might clear up a lot of misconceptions. Right, before I get to OOP, so hopefully I'll get after eventually. All right, so I want to talk about interpretation versus translation. Anybody ever talked to you about this in year 1? Honestly, I don't know what's been the course anymore. All right, cool. I expected the answer, but yeah. Anyway, I put up a bunch of languages here on this little left right scale. Moving to the left, when I say easy to program, I mean for you, the human, to actually come up with a program. Right? Difficult to program means you, the human, are going to cry many tears to make something. Add 1+1 in machine language? What? No! 20 lines later, it's right new. I have not added 1+1. Okay? If I had, you know, if I could be, I would smile and tell you back to you. What has been scratching? But yeah. Anyways, on the spectrum, whereas you can accept that Python is easy to program and with machine code, there is an efficiency problem under the hood, right? The efficiency has to do with interpretation. Now, we started this discussion as your programs have to run on a processor. And I prefaced it with, is your processor the same as my processor? Even for the same program you built in Visual Studio. You might have Horizon, I might have Intel, I might have an Intel 9, you might have an Intel 11, whatever number. Again, different instruction sets, right? So at the end of the day, the Python, Java, C++, do they turn into ones and zeros? The question I'm going to ask. At the end. Often the answer is no, not all. So that's where translation versus interpretation comes in, right? Our goal for a language like C or C++ is to translate it into machine code, which means that when you actually go through the build process, the ones and zeros you have coming out, you'll have an nice little .exe on your computer, which you could actually run, right? That exe has to be interpreted by the actual processor, because the ones and zeros for the processor itself. So therefore, the ones and zeros that comes out could be interpreted by your processor versus my processor. So there's actually multiple programs, if you will, under the hood, technically. So the build tool in Visual Studio has a hard job in when it is translating it for the processor, because it's not translating it for just one, it's translating it for multiple. Cool. So that's one area spectrum. But when you translate for the processor itself, the processor actually knows it's instructed. Oh, move, I know how to do that, I do it. Right? The other thing you could do is instead of translating it all the way to machine code, is translate it halfway down. Right? So take, for example, a language like Java. Java is not a language that will end up being something specific for processor to run, right? What it will do is translate it into another language. It's called Java bytecode, right? It looks kind of like machine code, but it's not. And that's because when you compile, build, guys might use the term wrongly. When you build that Java program, it is not run natively by the processor. There's actually an interpreter that sits between the built version of your program and the processor. It's called a runtime environment. So you have if you have here about Java runtime environment, that is something that is just running in the background. It's another program, and your program is just interpreted by that program. Be like, processor wants you to do this. I see in this line here, do this to me. Oh, I see in this line, okay, you do this to me, that processor, right? So the interpreter is something that people wrote. In the case of Java, it's runtime environment. In the case of Python, it's the Python scripting environment, right? Those things don't become machine code itself. They become something that is in between, which you need an interpreter on your computer to actually translate it for your processor. And it's because you have that extra piece of indirection, that interpreter, as to why it's never as fast as a compiled language. Right? Make sense? Yeah, you always have that little interpreter in between. Right? So the interpreter is actually a language with it. Well, that's a program which executes other programs. I need to have that. Language translation, on the other hand, means we're translating from one thing to another. Typically, when we say translation, we mean into machine code, right? So in general, you want to pick a high-level language when efficiency, meaning your runtime and your memory performance and that kind of thing, is not critical, right? If you have some kind of criticality with performance, you want to translate a low-level language first to improve your performance in general, right? Because the closer it is to the machine, the easier it is for the machine to actually run it, and the less interpretation that needs to happen by an interpreter. Okay. So an example of an interpreted language, again, is like MATLAB that we have done. You can't run a MATLAB script unless you have MATLAB on a computer, because you literally need MATLAB engine to run it, right? A language like C or C++, it's a translated language. You will get machine code at the end, right? Depending, right? Python, on the other hand, if you write a Python script, you need the Python interpreter on your computer to do it, to actually read the program line by line and interpret it for the computer. Can we write one interpreter? Actually made the ones and the AI did it write one for me, but so we can, yes. Just think about what the interpreter has to do. You have the Python script or the JavaScript or whatever code. Its job is to read the first line. Okay, this is what I need to do it. So read from a file, read a line, see what a line says, do it. Over and over and over. Get the next line, get the next line. Can you read it from a file? Yes. Can you read one line from a file? Yes. Can you do an if statement to see, well, which one of these things does this line look like? I'm doing. Yeah. So yeah, we can write it, yeah, but maybe you guys can. I don't know. Right? Sometimes people choose to interpret machine language in software. We can have like a simulator, for instance. All right, let me not go down this road. All right. Yeah, I won't go into these details. I stole these slides from a year. I did this a long time ago. This is from the year last taught this course. Not important for you. Right, good. So now that you have the rough idea, what I want to take you through is the steps of translating a program into machine code, meaning the program that you would have written, how to perform that machine code at the end, right? So stop the slide for a sec. If it ever chooses to stop. Hide. Stop the share for a second. I don't know why it didn't let me come out of it. Right, good. I'll back that up for a second. All right, here's a nice little program I started writing here. I'm gonna reshare the screen. Right, so tell me what this program does. I mean, it's pretty readable, I hope. I'll just type this. Did I actually build it? I don't know. I put you guys over here. All right, so if I hit build on this program. All right, notice the word it uses is build, right? Yeah, not compile. I mean, we use keyword compile kind of loosely to mean build sometimes. That's not actually true. Once upon a time, it used to wrap all the tools into one, but nowadays they can't, right? So sometimes you'll see words like build, or you might see a word like make. Because under the hood, what actually happens is that you invoke several different programs. You invoke a compiler, you invoke a linker, might invoke an assembler, might invoke a loader under the hood. Sometimes might invoke a simulator or something too. Right, so I go into the main steps. So you see, this program hasn't built. So that means somewhere on my computer, I wonder if I could actually find that. Let me try. Where I think if you click on this thing somewhere here, you might find where this program is. There we go. X64. bunch of logs. How did I build this now? First export. Anybody see exe somewhere around here? Is it in here? Ah, here we go. Here is the exe file that we generated. So when I built in a video studio, this thing pops up. I'm guessing it will do the program for me. My best guess. So do I need Visual Studio to run this? Then if I double click on it, would it work? Doesn't look so. Nope, not working. The reason it's not working is because this thing is what we call a Win32 program, which means that it's supposed to be executed on a DOS window, really and truly. So I guess my computer is a little too fast. What would have happened is Windows would probably create a Win32 existence, it would have run, and then it would have closed it off, and you probably wouldn't see it. But let me run it using DOS, and you'll see for sure. Not DOS, sorry, CMD. All right. So you ever use this command window? Assume.
I don't know what you're but mine is not debug at all.
Not debugging.
Yeah, it open up like that and see nothing. Like even if I set that breakpoint and I started debugging.
I have to see the check, right? So I'm using a command called CD. So CD is actually a program. If I go looking in System32, for instance, on my PC, I'll see cd.exe somewhere. Oops, CD is right, good. So I change the directory to here, and then if I do dir, I could cd exe there. So if I just type it in ecng exe, ran and nothing happened. Oh, right, because I have no CNC out. Therein lies my problem. Right, if I'm putting a C out, hash include stream, and now there's oh sorry, cd cout c, and the right. I'll rebuild it. Yes, please excuse the terrible program writing because I'm stuck at this. Oh, there we go. Yeah, when I go quick in there. Not too visible, but hopefully you can see it. Right. So you see, I could actually run the program just from this dot. I don't actually need Visual Studio to do it. I mean, just more convenient for me to click a button in Visual Studio and have Visual Studio do it. But the idea is I can actually create these programs and Visual Studio do it. Right. So on to the steps involved, right? So the first step was preprocess. I'm skipping that for the moment, right? I'm knocking this line back off just because I don't want the program to be too complicated yet, right? And I want you to tell me what would happen if I remove the semicolon. Won't build. Everybody's in agreement with that? There we go. All right. What did that mean? It didn't build. I mean, obviously it's missing a semicolon. We know it didn't build because it's missing a semicolon. So what I'm trying to ask is, what is the compile process trying to do? I think I answered it at the start. It's not a complicated answer. Yeah, it's machine code more or less. But what it's complaining about here is that it's saying, well, you didn't write my legal code, so I couldn't do translation. Right, that's literally what it's saying. I can't create machine code from this. Right? So let's be more clear now. What is it using to create the machine code? It's using the CPP file, in this case, it's called source.cpp, right? So the input is source.cpp, and the output is the machine code, right? For the compile step, right? That's not entirely true. Technically, the machine code it does is called an object file, which is an in-between step, but let's go with that for a moment. so that it will fail if it can't do it, right? If we haven't written legal code. All right. I'll go and try something else, right? This will now compile because sorry, this will now build because I put back any semicolon, it succeeds. But what if I cut this from on top here and put them on the bottom there? Will it still build? Let's see. I got a year. Yeah. Hmm? Does it tell it? Why?
Because you have a phone.
Have a weird one is out of the question and out of the function as well.
So I want you to think about what this thing is doing, right? This thing is translating from one language to the next, right? So it's a thing that's reading it line by line and trying to come up with, well, what do I need to write to do it? So if I read like, okay, line 5 is the first after line and reading, it's like, okay, this is meaning, okay, I know what to do with that. This is a variable called A, I know what to do with that, da, 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 da. I reach line 10, average. I don't know anything about average. I never seen this before. So you see reading top to down, top to bottom, that's a compiler does it. I never come across that. So I see the average, okay, I'll mark it afterward. Okay, I know average is a function, but am I going using this thing correctly? So it's worried about, well, okay, I don't know what this is. Let me not guess. Guys, stop in here. I don't know what this thing is. Right? So the way to clear this up is either write this thing before or write a declaration before, for instance, right? So if I copy this line, for instance, this is called a declaration line. Yeah. It will build now, right? It will build, right? Okay, why does it build now, even though it doesn't have all of the information at the start? Well, it doesn't have the body of the function, right? It doesn't have what one line is being used. How the function moves. It just has the prototype. You notice it works still, right? So why does it work with prototype? It has to do with the nature of the compiler, right? The compiler is, again, I'm just translating this line. When it gets to line 10, it says, well, oh, okay, average is the function. I can see that. You've given it an A and given it a B. You've given it two things. So all it needs to know is, well, how many things does this function call need? It needs two things, two unsigned int. You use it correctly. Okay, cool. It's a function call. I don't care what this function looks like. Sorry, I don't care how this function operates. I just care about, can I translate to a line of assembly? I can. It needs to be a call in assembly. And this is how the call has to work. It has to have these two unsigned integers before call. And the story, that's all I need to know as a compiler. Right? Are they unsigned ints? Yes, cool. They're going to give me an unsigned int? Cool. I understand how to deal with that. I don't need to know how it works. So much so that I could actually raise this A and B in this prototype and it'll still work. See, it still succeeds. It didn't even know what the variable to call. Right? It just needs to know, well, it has to be two unsigned ints. Right? That's pretty much it, right? You see how that kind of works out, right? So far so good. Let's get a little complicated. Let's create another file. Let's call this file a C++ file, and let's call it I have to call this boy. Let's call it average. Yeah, there's another C++ file there. What if I grab this guy from here and threw him in there? Would it still work? Create a function through the next file, right? An execute file in the same project. So will it work now? Yeah, let's sign up. I hope it was something. Yes, good. I can explain that. If it didn't work, I'll be like, damn it. Okay. So now let's think about what it does now, right? So now I am the compiler. My job is to create object code, right? I'm going to have a different definition, right? I talked about assembly and I talked about machine code. Object code now means specific to a single file. It's not a complete program, but it's specific to a single file. So you see each CPP file, what the compiler actually does is on each CPP file it finds, they're going to take that file and create an object file out of it, right? Usually object file like a .cpp is either .obj on some systems or .o, right? Depending. I wonder if we could see the object file. Let's see. Nah, I probably erased it. Maybe in one of these side directories it might be. Well, here's the average on the source, but I'm not seeing it in here. There's probably a setting in here which I could use to, oh, here we go. I found it. The average of OBJ and total OBJ. So in between, the compiler created those files. I don't know if you guys ever had me walk up behind you in the lab, and for some reason we just not doing the right thing, and it's like, why is this thing not working? You may or may not have had me do this to you, hit this clean solution. Yeah, what clean solution does is it see those intermediary files, and it just erases all of them. So just like halfway to the result. The result that we wanted is that exe file at the end, but in the process of creating it, the compiler is going to create an object file for each one of the files. And sometimes when it has to go back, it sees, well, oh, okay, I created this already. Let's not bother with that. And meanwhile, someone a old piece of code, and that's why it's not working, right? So the takeaway wanted to happen is the compiler is operating and creating an object file out of every single one of the CPP files in your project, right? That is the intermediary step that it is configured. Okay. The next step come into play after that, after you get each one of the object files, because we have multiple files now, you have to have a next program step in, and that program is called a linker, right? The linker's job is to be like, well, here are all of the object files. I'm going to go looking to be like, fill in the gaps and make this final machine code. So it's going to be like, okay, main we talked about, okay, let me put this one up here because it has name. All right, I see we talked about a function called average. Where is that? Okay, look at all the object files. All right, there's the function called average. Then I'll pull them in and put them together, right? So then the linker might complain if you can't find it. So if I were to remove this from this thing, you might get a link error. So let's knock it out. I just comment a note like that, right? And let's see if I could force myself to get a link error. So build, hopefully it cleans it. There we go. Watch the error you get to now, right? The no longer compiler, it says link, one unresolved external. So it says, I see a symbol called average. I don't know what the heck that is. Can't find it. Right? So it's either a difference between a linker error and a compiler because the linker comes after the fact, after I've gotten all my object files, can't find the thing. Right? That's the difference. Yeah. So in a similar vein, right? Okay, so you understand the difference between a compiler and a linker. I'm gonna put back in this guy. Oh wait, sorry, where you going? Take back off the comments. Get a little bit more complicated again, right? I'm going to introduce another concept. Add an item called a header file, right? Let's call them average.h as well. You see this? This file got created. Oh, okay. Ignore that hash pragma once for the moment. I'm going back to this, and I'm going to take this prototype now, cut you, and let's throw him in this file. Yeah. And then I'm going to write hash include average.h. This should be fine, I think. Yeah. It will. So the question I have to you is, what does this hash include be? Well, this is a preprocessor directive. Anything with a hash in front is a preprocessor directive. So if you have like hash define even, you have something like that, and I could just do, yeah. Right. So you might have heard people talk about the fancy term called the preprocessor. Right? The preprocessor is what we used to call when I was on the draft terrorist. Right? Okay, I suppose the terms have gone out of existence. So a draft means somebody who gives you a solution, somebody else. That's a draft. You're gonna copy paste that. So basically, the preprocessor, all it knows how to do in life is copy something from one place to the next. Copy and paste. So here I have to find the preprocessor before anything else runs, before you compile and before you link. All it does is it takes something and copy and paste it. Right? And as though the previous thing doesn't exist. So what they'll do is create a new version of CPP file on the hood when you copy paste it. So that hash file line will disappear. And everywhere you see 12 in the file, the thing that comes after 12 will be pasted there. Right? That's what the hash defining does. Similarly, hash include is also copy and paste. So what you do is you copy and paste an entire file, the contents of an entire file, and you paste it in right there. So you see that file called average at h. When you see that line hash include average at h, it actually takes everything we content that file and paste it right there. Right? That's all that the preprocessor does. So the preprocess create all of the CPP files, you'll get rid of the header file. You don't need it, it's not actually something that's part of the compile process. Compile will then run on your CPP files, one after the next, create all of your object files, and then last, your linker will come in and put your object files together. Right? That's actually what happens, and then that's how you get the EXE and the X. Make sense? So if you want to actually break up a project, that's how you would do it, right? You create a prototype, put it in the header, and you create all the multiple CPP files. Yeah, and that's allow each one of the things to work. Now the only thing is, you see this hash trackable once. Sometimes you might see something like if and def, hash define, blah blah, which is called a guard. This thing is called a guard on the header file. If I were to copy and paste this into the header file, what do you think would happen? I won't do that, but what I'll do is I'll copy you from here and I'll paste you in this file over here. That's to show something, right? Actually, I'm not too sure what will happen, but we'll see. Assume there'll be a linked error. Yeah, here we go. It's a linked error right now because the linker says, well, okay, I found average in this file and I found average in this file. It exists in two places, so which one you want me to use? Make sense? If I instead didn't have it in two different files, and I just had it in one, for instance, what do you think will happen? I think that's a link error. Don't think that'll be a link error. Yeah, you'll get compiler, right? Because it'll be like, well, I have two of these, right? Because the compiler is in that ran and so two. Whereas it was, instead, if it was in two different files, linker would have complained because it says I have two. These different, so two complaints, right? Sometimes when you're copying and pasting, your preprocessor can give you a problem because if you have a function body in the header file itself, if you hash include that in multiple files, in theory, the preprocessor would have put it in multiple files and therefore you'll get either a link error or compiler. And then you'll get multiple copies of it because again, the preprocessor is just copy pasting all over the place, right? Yeah. All right. So I think I've covered the general thing that's in these slides. So I'm gonna do a quick once over on this then. So let's go it over. Right. So here are the steps. You would have a program like, okay, I think this was a diagram for a SQL, but same thing really. we have the compiler runs, and in these guys' methodology, what they decided to do is say, well, the compiler is not going directly from high level C or C++ style code to directly to object code, right? They said, well, let's just translate first to a lower level language, meaning assembly. But they're going from the higher level language to assembly instead, which is still human readable. But see, we're still doing a language translation here, right? And an assembly code will just have, well, literally assembly. And the reason you might want to do that is if you're targeting multiple chips, because you might have to output assembly for Intel, output assembly for your Ryzen, or whatever chip you're using, right? And then you might have another program called an assembler, which works just like a compiler, more or less. Yeah, which will take now the .s file or the .asm file and then create the object code from that. So you can either go using a compiler directly from your C or C++ directly to the object code, or you can take an intermediary step and make assembly code, and then have the assembly file do it. Right? I wrote that to you who understand micro:bit, but I'll skip it saying your right. Ignore this, I'll talk to you about this when you reach micro:bit. Not important for things that will discuss that in the back, right? I don't go into these details too much, right? Next, we would have the linker. Now, here's the extra thing I was not telling you about with the linker, right? So far, you saw the linker operating as though we have a bunch of the CPP files that I created, and therefore a bunch of object files that I created. Well, what happens if I hash include iostream? Yeah. iostream wasn't a CPP file that you created, right? Which means that it's somewhere else on your machine. So technically, the linker does is it looks for stuff you create as well as stuff in standard directories. So here's a stupid question. Should those files already be compiled, or should the compiler, or should you invoke the compiler at that point? Would you find an iostream.cpp somewhere in your machine? No, you probably have an object file already created. So they don't make sense. We already know there's a bunch of standard code, create the object file already, right? There is one extra thing, I don't have to talk about it. What I've been talking about here is what you call static linking. It means as we have, since we are creating the executable file, we take all of the code and we bunch it into that executable file. Right? That's what we call static linking. Meaning the linker at this point in time when we are building, we create the XE and it's full of all the code we'll ever need. Right? There's another concept known as dynamic linking, which means that you don't package all of the code in your exe, you package some. Yeah. The reason you package some is because you see those same standard libraries. Those libraries, like your program and another program, could possibly use cout. Your program is not necessarily the only program using cout. So what the OS and the compiler makers do is they create what they call dynamic libraries, which means that your exe doesn't have all of the code, has some, but there is something else that's sitting on the machine with the rest of how cout is supposed to work. And while your thing is running, Windows or whoever else will call in that library on the fly and link it in on the fly. Right? That's what we call dynamic linking, but I'll get too much into that, right? So that's what linking is in a nutshell. It's going to take all of the object file and link it in the single program file at the end, right? So it's going to take each object file and creates your final output file. On Linux machines and stuff is .out. On Windows and stuff is .exe. Depends on where you are, right? On Linux is .o, on Windows is .obg. Object file. It depends on your machine, etc. Right? Details, nobody cares, details, right? All right, so the last thing in the step is your loader. So when you've created your final program, your exe and that kind of thing, when you double click on it or when you load it using the command prompt or stuff, that thing that is loading it has to understand how to interpret it, right? How to construct the entire piece of memory, where to put it. So imagine you are Windows, this program is coming into play. You have to know, well, okay, I have to dedicate some CPU time to this program. I have to do this program, then your program. I have to organize the memory. This part of memory will have to make sure it works fine for your program. And nobody else uses it except your program, etc. Right? And that's a loader in a nutshell, right? And I will leave that there. All right, that was my very, very